Well, hello, and welcome to another episode of Undercooled. Today, we've got a very special guest. We have one of our alums from our department, a man who many of you probably know, uh, Dr. Ray Decker. And so, Ray, welcome. And can you tell us a little bit about yourself?
Yes, I am a U of M grad, PhD, and since then I've been in industry, then a little bit in academics, and then back as an entrepreneur, but continuing as a adjunct professor at the U of M. And so I've had a varied career. I've been on the research bench 71 years, so I have a lot of experience I'd like to relate to this discussion.
So what year did you graduate as your undergraduate from Michigan?
1952.
And then you got your PhD here too, didn't you?
Yes,
And when did you get that?
1958. But I was in the service during the Korean War, so there's 2 years there before I came back for my graduate work.
And so, what did you do? What was your first job?
My first job after graduating was at a large company, International Nickel Limited, an international company in the field of nickel and nickel alloys.
That's great. And you were there for a while, weren't you?
24 years.
Wow.
And I went from the bench, inventor research, up through the ranks to be the corporate vice president of technology at Inco.
I'm sure we're going to hear much more about that later. But first, Tim's going to ask you a question.
Yeah. Before we get to some of the post-school stories, as a Michigan man, of course, the undergraduate materials education is the foundation for everything that comes after that. And what I want to ask is, as we have this sort of theme of learning never stops and learning how to learn, how did your undergraduate education prepare you to succeed?
It was very hands-on and backed by very good theory and very close relationships with the professors who had the objective of applying metallurgical engineering to solving problems. So I had the right attitude, learned the right attitude toward contributing to society. Then I worked half-time as I was an undergrad and got a job in the metallurgy lab as a sophomore. That's what really set me off in a very good direction with Professor Freeman.
That's something I think we still hear from our students today is they get into a lab and they start actually working and actually learning and saying, "Oh wow, there's a lot to be gained here." It's great to hear that that's a continuing story.
And I benefit from very fine mentors all the way through grade school, high school, and university. Very fine mentors who dedicated to improving my learning situation.
That's great. So, I want to start asking you about some things you did earlier in your career when you worked with International Nickel. And correct me if I'm wrong, but I did a little stint at Bell Labs, and I learned very quickly that Bell Labs solidified their business base by making sure they controlled all the copper in the world because their product was long lines that were made of copper. Whereas General Electric, of course, they wrapped up all the tungsten supply in the world. But it sounds like you guys wrapped up all the nickel supplies in the world. Was that
Yes.
the case?
Yes. When I joined Inco, we had 90% of the world supply of nickel. Yes.
Right. And so you told me some great stories how, International Nickel was always looking for products for steels that had nickel in it.
Yes.
And I think you told me the story of Inconel.
Yes.
Can you tell us that story?
Inconel goes back to the early history of the labs of Inco. Inco is short for International Nickel. And there was the usage of nickel for pots and pans and milk cans at that time. And stainless steel was invented and started to take part of the market. So Inco started a project to have a high nickel stainless steel. And the test was quite primitive. it was a test overnight in chicken gizzards. And if the samples were black in the morning, no good. If they were shiny, good. And as a result, the market never developed. They did not penetrate the stainless steel market. But amazingly, 40 years later, Inconel was adopted by the Navy for nuclear reactors, submarine reactors. So those chickens are really smart.
That's fantastic. So again, you've told me that you've learned many lessons through that experience. Can you elaborate on what students need to think about when they're doing one thing, how it might end up being really important somewhere else?
Yes. I believe very much in serendipity. I'll explain that a bit later. But also, like in basketball, you've got the target of the basket, but you need to have peripheral vision and watch the rest of the game develop, because you might turn out, rather than shooting, having an assist that allows another player to score. So I believe very much in following the literature, keep learning. And every month I go to the library and read the related literature, and I got a lot of good ideas from that then match the project I'm working on, and quite often develops in a different application, a different market than the original market. So I think it's very important to keep learning and do a technical learning operation every month, which I do now, even now.
That's fantastic. And then I guess you've also told me some stories about mortgaging steel, which you were very involved with.
Yes. When I arrived at Inco, I worked for a brilliant inventor, Clarence Bieber, and he had started some work on a new type of steel, no carbon like you usually have, but high nickel, 18% nickel. You get a much nicer martensite. That's a shear structure, and it's very tough. And then you can age that, precipitate fine particles in that martensite. So I coined the word bar aging to represent those steels. And the first steels were very brittle, and we had a task force to try to overcome that brittleness. And reading the literature, I thought that molybdenum would be a good addition to toughen the grain boundaries to get rid of the embrittlement. And then that lowered the martensite transition temperature, and then we needed something to bring that back up. So I thought cobalt would be good in combination with molybdenum. And that summer, this is 1960, I was fortunate to have an intern student from NYU, Alan Goldman. And within a couple of weeks, we discovered that the higher cobalt and moly had really spectacular hardening effects that we did not expect, serendipity. And that was the birth of the bar aging 18% steel, which is still used in that same composition that we found in 200-gram melts, still used today. And it went commercial in less than a year for missile cases. Alan Gold went on to be director of the U.S. Mint. So he had a very successful career, but a very brilliant summer intern relationship with us.
That is fascinating. And, I remember showing you once some of the student work in our intro course where the students make they design a component of a superhero costume. And one group chose Captain America's shield, and they used aging steel for Captain America's shield. And I remember you looking at all the values they had there and saying, oh, they got that right. They got that right. They got that right. They had actually read some of your work. So that was kind of cool. So even Captain America thanks you for aging steel.
That's another outcome was serendipity. I didn't expect that. But on markets, that was another serendipity, peripheral vision. Although we were aiming for submarine plate, it turned out that these other markets came along. So many other markets came along. Missile cases was the first one, but in the end, such surprising things as golf clubs and Olympic epis were designed out of mahogany steel, Russian Olympic epis.
Huh, that is fascinating.
As long as we're talking about these steels, I notice you have some specimens here on the table to show us. Could you tell us about what you have here?
Yes. Part of the surprising applications for mahogany steel was as bolts in Apollo 11. And as you know, after landing and exploring, Armstrong and Aldrin had to get back in the returning vehicle and separate from the platform. So there was a need for a very reliable mechanism to separate and leave the platform behind. So the engineers involved at General Atomics developed this explosive mahogany steel bolt, and it was redundant by exploding in two places. One place broke the bolt off here. The other place was the nut, which was exploded and expanded to release the nut and the bolt from that end. This is experimental sample 164, and just as an example of how thoroughly the components of that mission were tested before ever being used on the exploration of Apollo 11. And so I can say that one half of this is still on the moon. I don't know which half, but one half is still on the moon. And then there was another application, unexpected, where we have a component still at 16,000 feet in the ocean. And this was a CIA operation to recover a Russian submarine. And it was cloaked under the excuse of searching for nodules, nickel nodules in the ocean. And they suspended and dropped a cage device with prongs that were going under the submarine and then picking it up to the point of raising it into the surface vessel. And the K-129 Russian submarine off Hawaii was recovered by that operation, by the mahogany steel clamp. And there were many things learned about Russian submarines from that recovery. And I didn't find out till roughly 2000 that the actual thing was a cover for this operation. I thought it still was a nodule operation.
Wow. So besides Inconel and mahogany steel, what other things are some of the highlights you did while you were at Inco?
Well, we worked on a lot of different applications at Inco. We had a large lab. We had 600 people in R&D at that time, corporate R&D. And we had such projects as a new alloy for nuclear submarines, IN 690, the cast blades for turbine jet engines, Inconel 713, and actually the early project on the coin that you now use, the diamond quarter. They're laminate coins, and we did the basic work in our lab to develop the lamination of the copper core and the copper nickel surfaces of the dime and nickel. I'm sorry, the dime and quarter. Pardon me.
Yeah, I remember we had one of our other alums, maybe he worked for you, Jerry was his name?
Jerry Brophy. Yes.
Yeah, he gave a talk about the problem that you guys all solved that the Europeans didn't pay attention to. And they wanted to make a loonie type coin for the euro. And they never realized that the two different metals might create an electrochemical cell when you held them in your hand. And they started depositing metal on people's hands. But you had thought about this with these composite coins, and you wanted to make sure that the EMF potentials were the same.
Yes. We had to pass a sweat test, and the one you mentioned. But the critical test was to be able to use the coin in the same coin machine for the prior silver dimes and quarters. That required a combination of electrical and mechanical properties, and that was solved by having the laminate of copper and the copper nickel alloys.
That's
So
fascinating.
Jerry was the inventor of that.
That's amazing. So after your career at Inco, I remember you told me you went looking to buy IP in Russia. Is that right?
Yes.
Did I get that right?
Yes.
Can you, because I've met other people who also have gone looking for IP in Russia, and it's amazing how little most of those people came back with. Was that your experience as well?
Yes. Yes. We had a government contract, and my wife was my secretary at that time. So we had 6 trips to Ukraine and Russia to look for technology to bring back to the U.S. And we did visit half a dozen labs in Ukraine and Russia, and we identified a large number of projects that looked attractive. And we had the scientists come to the U.S. and present their results to the various companies in the United States and to the government labs. Some of the technology was brought over to the Navy and the Los Alamos labs, but the problem was that the institutes were very deprived, very depressed, had very low budgets, and the technicians who had made those samples had left, gone out on the street to sell cigarettes. So when an American company or organization wanted some test samples to check out the results, the labs in Ukraine and Russia could not make test samples anymore. So only a little bit of that technology came over. The principal one was physical vapor deposition, picked up by Pennsylvania, Penn State first. That was the principal outcome of that. But much of the other technology we're not able to bring back to the U.S.
And yet, I think you probably learned a lot of valuable things from looking for IP, because you then tried to translate that back here in the United States, didn't you?
Yes.
So another example of how learning never stops. Even though you didn't get what you thought you might be able to get, you ended up learning a lot. And I kind of know where you're going with this next story because it's amazing. So can you talk about finding IP back here in the U.S.?
Yes. I wanted to be an entrepreneur. After being in a large company, I got very attracted by being an entrepreneur. So I started a company here in the U.S. searching for technology at universities and organizations. And serendipity really came to play here. I arranged a meeting at Dow Chemical and had a one-day meeting at Dow Chemical looking over technology that they wanted to spin out of Dow Chemical. And most all the proposals presented to me by Arnie Geiser were chemical, not down my alley. So I said, Arnie, do you have any metal things you want to spin out? He said, well, yeah, we've just started thinking about a process for semi-solid metals that we've developed, and we're just thinking about spinning that out. Let's have lunch with Connie to learn about that. And boy, I thought that was a real nice magnesium injection molding machine. So right after lunch, Arnie and I made a deal that we would form a joint venture, Dow and my company, Thixomat, and commercialize this as far as we could. So we first thought about the auto industry steering wheels. So our original target was steering wheels with a target of 30 machines. Well, it developed in many other applications, again, peripheral vision, and ended up in many things, mainly electronic applications first, the Walkman, Sony Walkman, but the camera type that's looking at me right now. And most projectors use a system that we developed with Texas Instruments, a bench type electronic device, DLP device. So there's been a lot of applications there. But then things like Oakley sunglasses, UK2 snowboards, shaggy skis, finally ending up in knee braces. We got in the business of making magnesium for knee braces, working with a company called Donjoy. So they make the Nano Ortho knee brace that you can look up on your internet with those words. And we've made enough magnesium for about 300,000 of those. So it's a prime product of Donjoy Knee Brace Company. So that's Thixomat, which we went over a period of about 20 years with Thixomat, developing the commercial practice in 13 countries with over 600 machines out, making a commercial business, a new business developed by our venture, our entrepreneurial venture.
That's great. And again, serendipity. And I remember Teresa Pollock told me that it also happened that you kind of wrote the original papers on semi-solid molding way back in the 60s. Is that right? Or?
Yes. And Teresa was one of the co-authors, along with Wayne Jones, Tracy Berman, Tori Miller. So we had several very fine papers on semi-solid magnesium, yes, made by Thixomolding.
That's great. And I'll never forget, you brought me once to a factory that made plumbing parts with die-cast magnesium.
Yes.
And showed me just how loud, how noisy, how dirty. They had Led Zeppelin blasting over the top of all of this thing, and this guy was in like a leather vest but no shirt underneath because it was hot, and he'd pick up the ladle of magnesium. As soon as it went through the cover gas, it would burst into flame, and then he'd pour it into a machine and stamp on something, and then you showed me your machine that was quiet. You could use it in a shopping center. There were no toxic fumes, no cover gases. So from a sustainability standpoint and a quality standpoint of getting no porosity, your technique was just so much better. And so it just blew me away when I saw all that. So thank you for taking me to that place.
Well, that's a very good summary of the virtues of Thixomolding: the environment, safety, and low porosity, high properties. So you summed it up very nicely. Yeah.
We've heard a huge range of applications already for some of these things, but I understand some of what you've developed has also been very biologically oriented and has been used in a lot of human systems as well. So could you tell us maybe about some of the biomag or other
Sure.
related products like that?
Yes, and that's an interesting story of serendipity. As I'd mentioned, we first got into the knee braces, but a scientist at Biomet was wondering about magnesium implants, bone implants to fix bones. So she asked her father, who is in the business of making magnesium. And her father is John Parapesco at West Point, not West Point, Wisconsin. And he said, my former student, Steve, is the guy who knows all about magnesium for the possibility market. So Elizabeth Parapesco called Steve, and that's how we got started in making implants. And we've invented a special alloy designed for that very purpose. One that dissolves at the right rate, one that is not toxic to the body, and is strong, one that bone likes to grow on. And so we've got a very nice start in making orthopedic implants to fix bone. We've had some very good government contracts, NSF and NIH, to develop that business. And after we got into that business, again, my learning experience, reading the literature every month, the 15th of every month, I go online now with the Michigan system. I started seeing papers on the anti-cancer properties of magnesium, and mostly from China. But these papers pointed out that when you have magnesium in the body, it dissolves, it releases magnesium ion and releases hydrogen gas, and both are anti-cancer agents. And fortunately, we had used calcium, zinc, and manganese in our alloy to get the right properties. Turns out all those elements are also anti-cancer. So we got a very nice project started at the University of Michigan now with a very nice team working with Michigan and the VA. So we put together a team that I call a get-go team that involves the researchers, the clinicians, but also the end user, the VA hospital here in Ann Arbor. So we have that team of U of M, VA, and Michigan, and Nanomag. And we're working at the very early stages with looking at the effects of our magnesium alloys on anti-cancer. And the first results are very positive, where we put together, this again, Claudia Lobel, professor of material science and engineering, makes a sandwich with the two pieces of bread are mouse tissue. And then she puts the lung cancer cells on one bread and the wires on the other bread, puts them together, and for about $100 in 7 days, you get the results of the magnesium on the cancer cells. We call that the butter, the bread and butter with peanut butter and jelly sandwich. But it's a very fast way to get results. And we've gotten some very good results there. And now we're branching out into animal studies with mice and with sheep. And the idea of this get-go is to, right from the start, get all the actors in the game right from the start so that you get the best advice from the clinicians, from the end user, the VA, so you start in the right direction. And you should be able to compress the whole lengthy procedure to get to FDA approval by having everybody in the act right from the get-go. And by the way, that's how we started Thixomat also. Dow's requirement in the joint venture was that I find 4 other investors who would be users of the technology. We call strategic investors, and we did find 4. And those companies used the technology, but they also spent extra money in developing the technology. So there was a lot of power in having the right team right from the start, the get-go team of all the players, the researchers and the end users playing together right from the start. So I, of course, I'm a strong believer in the get-go strategic partner idea.
That's fantastic. So what kinds of cancers are you guys targeting?
Right now we're targeting lung cancer because that's the most serious. There are 2 million lung cancer cases a year, and half of those pass away. And amazingly, even with all the advances in cancer, the growth of lung cancer is more than 10% a year. But the Chinese work was on 13 different types of cancer. So there's a broad possible applications here that will evolve from the lung cancer results, such as ovarian, breast cancer, and liver cancer, 13 types of other cancer than lung cancer, which have been benefited. And one very interesting angle is the combination with cisplatin. Cisplatin is one of the most common treatments for cancer, and it's a chemical chemotherapy treatment applied by IV treatment. And about 30% of the cases with cisplatin develop kidney damage. And some of the Chinese work has shown that if you combine the magnesium with the cisplatin, you obviate, you prevent any of that damage to the kidney. So there's a very interesting, very exciting possibility of combining cisplatin and magnesium implants. So Claudia and Karen, our professor friends, are going to look at that in the next few months. By the way, one of the professors, Karen Ligasetti, is a practicing oncologist. He does 100 lung cancer operations a year. So he brings that experience and knowledge right into the game right at the start.
Are you developing alloys for this, or is this just pure magnesium?
This is an alloy. So it's an alloy I invented with magnesium, zinc, calcium, manganese. All those elements are operating on cells along with the hydrogen that is generated by it dissolving in the body.
But I presume you're using that because it's FDA approved.
No, it isn't.
It's not.
We've got to, that's the big challenge,
Right.
is to get enough evidence in mice and animals, then in humans, to go to the FDA to get approval.
Okay.
And that's another angle, getting VA in right at the start. They've got the patients already. They've got 800,000 veterans who are threatened by lung cancer. So they're right in at the start. They'll go with us. So we'll go to FDA along with the clinicians and VA. Much faster, much more convincing story. Much better tuned to FDA approval. So that's my get-go idea, a strategic partnership at the start.
Well, it seems like that's a big thread coming out in the conversation here is this leadership angle and
Yes.
having the right people with you, building the right teams to get work done. For the audience, especially, we do have some students who listen to this. What's some advice that you could pass along with leadership and with working with others and leading others and how to
Yes.
build an effective team?
Yes, there are several parts of leadership and learning. And one of the tasks is to learn how to lead. There are at least 4 or 5 types of learning, but one is to learn to lead. And you have to learn to partner with people. You need partners, so you need to learn how to develop partners. And but becoming a manager or a supervisor is not an easy task. That's a hard thing to learn, especially for an introvert like I was. You have to learn how to get things done through others. And you have to delegate and quite completely delegate, not try to get your fingers back into it, but give the responsibility to somebody to carry out a task, even though you think I could do it better than they. But you have to take the mindset that they can help you. They may not do quite as well as you could, but you can have several of these people working. You get a lot more done if you have a team and delegate to the team. And like I mentioned, you don't want to get your fingers back too much or try to compete with the guy you delegated it to. And some managers do try to compete, or they might assign the same task to 2 people to make sure that they keep complete control over it. But you need to delegate to one party and trust them to do better than you might have done. So that's one of the first things in becoming a supervisor is learning how to delegate. And then that brings up mindfulness. You have to learn how to be mindful. That is to look at the other person, get to know them by starting with some simple questions, like how's things going, or what was new to you last week. Something to get the conversation going with them, then participating and feeling like they're equal with you. So that's one of the secrets is to be mindful, get the discussion started. And then you have to respect them and continue that delegation to them and honor that responsibility that you've delegated to those. So that's a type of learning that you need to get over. It's hard to learn, and it takes some experience to learn that. And your first leading job is the most difficult one to learn that trick. But the higher you get in the organization, the less contact you have and the less technical contact you have. It becomes more a management responsibility of delegating. So as you go up the line, you have to learn how to be a manager. Very important one of the most important parts of learning.
It's very interesting because, as you know, the world has been going through what I think is a interesting revolution of understanding about inclusion and inequity. And although a lot of people get political about it, it's much deeper than that. Being inclusive means including everybody, no matter who they are. And
Yes.
so if you have employees, you want to include them in the whole process so that the company does better. And the more you trust them, like you said, and the more you get them to speak, because most people are introverts, like you mentioned, you have to draw them out and make sure that their voice is heard and included. And when that happens, most of the time, everyone on the team will start to respect everybody else. And to me, that's what real equity is, meeting everybody wherever they are and seeing the value they bring to the team. And so having this as part of our core educational principle, which is starting to happen, I believe, in most educational institutions, I think this is going to bode very well for the success of companies down the road.
Yes.
Because you're right, it's a very hard skill to learn. You know, we do it by doing team-based teaching. We teach our laboratory courses with teams. We teach our capstone design with teams. We have all of our teams, you know, solar car, et cetera. And I just think what you're saying is so important. These are the kinds of skills we need to teach our students how to do now, so when they get into leadership roles, they've experienced it firsthand.
Their students are much better prepared for partnership and leadership now than when I got through school. But I was lucky. I grew up on a farm in a small town in New York State, and most of my classmates were farm boys. We all went to work when we were about 10 years old for our fathers. We had tasks to do, but we had a hired man who didn't have any college training, never finished high school, but I learned far more from Nevin than a lot of other people. He taught me a lot of hands-on tricks and how to get the job done the same day, how to fix things. So by the time I started at Michigan, I had a great respect for that type of person, a hands-on person, even though not well educated. Then in Michigan, I took ROTC, so I was an Army officer in the Korean War, not in Korea, but France. But I had a lot of non-commissioned people, women, steno pool to work with. So I learned to work with a lot of varied people, a lot of varied positions, varied education preparation. So that I was quite well prepared to work with a broad type of person by the time I got to INCO. So that's a very important thing. One thing we learned at INCO, my boss taught me this, Clarence Bieber taught me this. The very first day I was there, he said, use the best theories you got, sit at your desk in the morning and plan for about an hour. But put in your orders for tensile tests, belts, and like that. But don't sit at your desk. Get out in the lab and watch the experiments. And you'll learn more by watching the melting, the rolling, the tensile testing, creep testing. You'll have serendipity, and you'll observe things that you never would see if you sat at your desk. And the other thing I found from the technicians, Clarence also taught me to talk to the technicians who are doing that job, tell them what you're doing, what your objectives are, get them involved in your experiments, and you'll get much better service from the technicians. And in fact, they'll put you at the top of the list. They'll do your work before the other guys who are sitting at their desks. So I'm very much a believer in getting into the lab and observing.
That's fantastic. And making everybody feel like they belong
Yes.
and are part of the effort to make the company succeed.
Yes. All are part of the mission. Yes.
Yeah.
That's something I also hope that we're starting to succeed at more with our students as we're teaching, to make them feel like they're part of something.
Yes.
That
Yeah.
they're belonging to a bigger mission, that we're trying to accomplish things together. Just like the lab techs, who are doing the metallography, if they can see I'm contributing to something. My work makes a difference. It means something to someone.
Yes.
Of course, they're going to be more involved. And I hope we're starting to give our students that same perspective.
To know the end use and the practicality of what they're working on.
So you've also done a tremendous amount for the community. And I know your work with ASM Foundation's something that's just a, real passionate labor of love for you. Maybe you can talk about, how you like to give back.
Yes. And that's another type of learning. I call it learning to give. Early in our careers, in our childhood, we're taught, we take. But it's very important to learn to give. And one of the ways I've done that is through the ASM International, the foundation of ASM International. So I've been working with them for about 20 years. Most important activity is teacher camps, where we have high school teachers come in, middle school teachers come in for a week training, starting at the University of Michigan, but there are about 45 of these a year at various universities. They have a 1-week course on hands-on lab techniques. And it turns out that about half the high school teachers do not have science training. They have good education training, but they're suddenly assigned to be the science teacher. So they're not very comfortable in the lab. So our purpose is to teach them simple experiments that get into the hands-on exchange of samples with the students. But they leave with a small kit, a lab kit, costs about $300. We pay for that. But it has steel wire and plastic samples and such. But when they use those up, they go to a local hardware store and buy the replacements for $10. So this has helped out. Many of the schools have a very limited budget and can't afford a fancy lab and fancy equipment. So we've trained some 12,000 high school students under this MEF, Materials Education Foundation for Teachers. And I was lucky to be chairman of that foundation a couple of years, around 2009. But I stay active and participate very much and have a lot of fun being part of that foundation.
That's great. And, this summer we're having the North American Materials Education Symposium here in Ann Arbor. And when we talked to Chip Keogh a few episodes ago, we came up with the idea of maybe bringing some of the alums of our teacher camps from
Yes.
the local area to come and interact, be part of a get-go team with us, with the educators, so that we understand how they're using that in their high schools and creating modules for their physics or chemistry courses, or how they're even teaching a materials course, and then maybe how we can engage with them to have them help us recruit really good students from their high schools. So hopefully you can come this summer and
Oh, yes.
and contribute to this, because I think it's going to be a lot of fun. So it's August 7th and 8th. So hopefully you'll be around.
So I'll be there. And interesting observation. The best time to attract students is in middle school. And especially with the boys, they are much more susceptible to engineering, science in middle school than when they're a junior or senior in high school. And the response of girls has been very pronounced. We're seeing a very strong reaction of girls who want to get into STEM. And we can see it here in the classes. Really very fine women students here at Michigan, elsewhere. And going back, telling old stories, in my graduating class, 1952, there were 500 engineers at Michigan, and there were 3 women students of the 500. And now, well, I think, Steve, it's 35% or so.
Yeah.
And they are good. They are really fine
Yep.
scientists and engineers.
They are.
Yep. very good contributors.
So we still have a little ways to go, but we're getting a lot closer. And but what you said is really interesting. We need to focus on how do we target students to deliver the message at the right time in their middle school or high school career, so that we can really convince them. And one problem I'm having, I can convince the students, but then their parents tell them, no, you can't do that because mechanical engineering is a broader field than materials.
Yeah.
And I'm like, no, it's not. Materials is a much broader field than mechanical engineering.
Oh, yes, yes.
And how do we connect with the parents and their families to make them recognize? I mean, here at the University of Michigan, over a third of our research expenditures as an entire College of Engineering is materials research.
Wow.
And yet the material science department, we're only 24 fully wet faculty out of 650 faculty.
Mm.
There are more material science faculty, they were trained as material scientists who are on the faculty of mechanical engineering than our whole department.
Mm.
And so that's this outsized importance of materials to all engineering. And it's like, well, duh, you got to make it out of a material. And
Yes.
material is usually what prevents it, puts the limits on the performance and the innovation of what you're going to do. So if you don't study materials is that broad.
Well, it's very broad through most industries, even highway construction depends very much on control of materials and materials properties. But I have a story there. My son-in-law, Rick Colson, worked for Intel, and he was a senior fellow at Intel, just retired. And he led the team that developed the solid-state drive. So I asked Rick, what was the secret? And he said it was a materials invention, using hafnium to get less diffusion. But the use of hafnium material was the key to the solid-state drive, a materials problem solution in the electronic computer field. So we've had several graduates go to Intel, but just an illustration of how broad the fields of application job opportunities there are across many industries. The materials spread through most industries.
Yep, absolutely.
Even forestry, yes, highways.
Well, even wood is a material. We've been using that for a long time. And I'll never forget when I built a deck at my house, I was perplexed with the problem of, do you put the planks down grain curvature up or grain curvature down? And I didn't know, I saw all this conflicting stuff. So I went and found Larry Van Vlack, and I asked Larry, and he just looked at me with that little twinkle in his eye and a little chuckle, and he goes, yes, it's interesting, isn't it? And then he began to tell me all the, pros and the cons. And his advice at the end of the day is, it doesn't matter.
That reminds me, one of my episodes, I was up at Michigan Tech as a VP of research for 4 years. And one of the projects we started was cloning of the European larch tree to make them grow much faster, to make better and more lumber. And that was a very nice biotech project that succeeded. And that was a very special cloning technique developed by the forestry bio people. Another interesting application of materials and biotech.
And now everyone's trying to take wood and remove the lignin from the cellulose to do all sorts of other things with it. And even in our department, Alan Taub, even though he's the head of the EV Center, that's his research, figuring out how to, use industrial hemp fibers for, all sorts of applications. But it all comes down to getting rid of that lignin.
Oh.
So it's like you said, the longer you do this, the more serendipity plays and the more interesting and unusual areas you end up doing stuff in, even though none of us were trained to actually do this. It's how we learned how to learn that was actually the most important part of our
A
education.
very important asset to carry, to renew, broaden out. One thing I wanted to caution, I've been in research for 71 years, and you have to learn after you become 80, stop preaching or warn the listener to take what you say with a grain of salt. So I wanted to express that point. I have expressed experience and advice, but please, I'm from another generation, the silent generation growing up in the Depression, World War II, and the Korean War. And my background is much different than yours as new students. So I don't pretend to know just your background. So please take my advice with a grain of salt and not as an absolutely to-do lecture. Thank you.
It is very good advice, I think, for all of us to remember that our students are quite different than we are. But, there are some things that I think truly are constants across generations. And one of them is this idea of investing in your own learning
Yes.
and learning as a way to invest in yourself so that ultimately you can accomplish something important and give to society instead of just taking. So I guess, do you have any last thoughts on that investment in yourself and how
Yes.
your learning is accomplishing that investment?
Most certainly. And first, I'll just state from my background, despite what you hear over the news and newspapers, things are a lot better now than they were in 1930 and 1940. And another thing to think of is your life expectancies will be longer than ours. So you have a chance to give and contribute even after 65. So that's one of the benefits of reinvesting in your learning. You can learn some new tricks that could lead you to very good activities contributing to society, giving, even after you retire. But you'll probably work longer than 65, which is now, of course, the tradition. But that's a very positive thing. And I'll tell you, it's a lot of fun to keep learning new things and working on new things like this anti-cancer thing. That's the most fun of anything I ever did.
That's awesome.
That's wonderful.
All right. Well, thank you so much for coming and talking with us, Ray. I thoroughly enjoyed it, learned a lot, and
Very interesting.
I appreciate it. So we'll say goodbye now. So thank you very much, and thank you to our listeners for listening.
That's right. We'll see you next time on the next episode of Undercooled.
Thank you very much for the opportunity.